Welcome back. Today we're going to discuss the topic of ignition and extinction. Okay, you all recall example 8.8 where we were designing a reactor for the production of propylene glycol, and this reactor, which is a CSTR, is to be operated adiabatically. So we did this exercise and we actually we're gonna find the temperature and the conversion in that reactor, which had the volume of 300 gallon, and we had to solve this by solving the energy balance and the material balance simultaneously. Then we went to example 8.9b, where again we were looking into the adiabatic CCR. However, the feed in this reactor now was at a temperature of 70 degrees Fahrenheit, and here we found that we had three steady states, right? Three steady states. And we found that when we plotted the conversion found from the material balance and the conversion found from the energy balance versus temperature, and where they meet, that means this is a steady state, because both of these equations were derived for a steady state case. Okay, we can actually solve the same problem by solving the combined energy and material balance, where we can plot GT, the heat generated, and the RT, heat removed, versus temperature. Again, we can see that we have the same three steady states. Okay. طيب. With this brief introduction, now we can go ahead and talk about ignition and extinction within a reactor. Let's take a CSTR. So let's consider an adiabatic exothermic reactive system. And basically, this reaction is carried out in a CSTR, as I just mentioned. Okay, let's plot GT and RT versus temperature, just like we did earlier. So GT equals X in B, X, the conversion found from the material balance equation, times minus delta H reaction, and both of these are function of temperature. And the RT is here the summation of theta I CPI times T minus T naught minus Q dot divided by FA naught. And in this specific case, we said we have an adiabatic reactor, so therefore this guy goes to 0. Type. And RT here, if you look at the RT equation in this case, if we have the average values for CPI, you can see that we have a equation of a straight line. Okay, equation of a straight line where you have a slope and you have an intercept. Type. And let's look here to the right. This is the GT. We can see the S-shape curve, and this S shape is coming from the shape of the X in B, which is X in B versus T, right? The S shape. And if you look at this straight line, these are the RT. Okay, this is the RT, and you can see, as we said, it's a straight line. And if you notice that the value of RT, goes to 0 when T equals T naught. So let's take this RT. Okay, this RT is line of RT, a straight line. And when we have RT equals to 0, basically, when this guy goes to 0, that means the value of T. So let's read the value of T. Where do you read the value of T? This is the value of T for this line. Okay, so this is the value of T here. Okay, it's basically equals to the T naught. Okay, and in this case we have T naught 1. Okay, let's now change. Let's change T naught from T naught 1 to T naught 2. So basically here the slope will not change. However, the intercept will change. Okay, so the slope will not change. As you can see, the straight line B here is parallel to straight line A. Okay, but the intercept changes. Now here this value where T equals T naught when RT equals to 0. Okay, that's where the difference comes from. Okay, very good, very good. Now, as we said, we can continue varying T naught. Okay, and when we vary T naught, does GT change? Obviously, GT will not change because the XMB and the minus delta H reaction are function of T, not T naught. Okay, so this will remain the same. However, what changes is basically the RT. So the RT will change because it's function of T naught. Of course, the slope will not change in this case. Okay, the slope will not change. That's only the intercept will change. And if we vary this, then we get different steady states. For instance, let's look at the curve for RTA. Okay, this is the A curve. And this is plotted for the case where T naught equals T naught 1. How many steady states we have? Well, it's very clear that we have only one steady state here. And how do we read the steady state temperature? Well, basically we have to go vertically down. Okay, and this value is simply, as you can see, the value of TS1. And what about RT and GT? We can go horizontally to the left, and this is the value of GT and RT, which are equal because a steady state RT equals GT. Okay, let's change the T naught from T naught 1 to T naught 2. Okay, you can see here. Now we have T naught 2. Okay, and let's read the steady state points. Well, this is one steady state, and this is the other one where GT equals RT. How do we read the steady state temperatures? We go vertically down here. In this case, this is TS2, and for this case, we go vertically down, and this is TS2. So we have TS2 and TS3. Sorry, TS2 and TS3 for a case where the T naught equals T naught 2. So if T naught is increased from T naught 1 to T naught 2, as we explained earlier, the RT curve, these are the RT curves, okay, will intersect. Now this is the new RT curve, will intersect with the GT curve at point 2 and will be tangent at point 3. So we have here an intersection, intercept, okay, and here we have a tangency. So leading to two steady states. What are these steady states? Let's see. This is two steady state temperature, TS2, and this is the other one, which is TS3. So now that this is clear, we can go ahead and vary the T naught even more. So continue varying T naught and record the steady state temperatures all along. So let's do that. You can see the curve now. Here we have A, B, C. All of these are the RT curves where we are changing basically the T naught values, and we're getting different steady states, right? You can see here 4, and then here 5, and then here we have 6, and so on. Okay, so that's the table. When T naught equals T naught 1, we had one steady state, which is TS1. Okay, when T naught equals T naught 2, we had two steady states, correct? When T naught equals T naught 3, what is that? I'll just explain that, I think, just now. This is T03. Okay, we had 3 steady states here, as you can see. This is steady state 4, steady state 5, and steady state 6, and we can read the steady state temperatures. How can you read steady state temperature? You go vertically down, right? And you read the steady state temperatures. Okay, so basically here we have TS4, TS5, and TS6, and we continue doing this exercise until we get all the steady state temperatures for all of these studied or varied T-naughts. I don't need to remind you, but you know that both the mole and energy balances are satisfied at the points of intersection or tangency. Okay, so both equations are correct, or both equations you have in each equation left hand side equals the right hand side. طيب. Now let's plot TS versus T0. Here we are. Let's do that. So let's plot TS, which is the reactor steady state temperatures, versus T0, which is the entering temperature or the feed temperature. Okay, so for the first case, okay, where we have T01, which is the feed temperature, we have here one steady state temperature. So let's see, this is T01, right? And this is TS1. So let's plot this. Let's go up like this and here, and here we go. This is the point. Okay, this is the first point. Let's plot the second point. So this is TS. Let me change the color. This is T02, and in T02 we have two steady state temperature, TS2 and TS3. So we go vertically up here for this T02, and let's see, we have then TS2. This is TS2. Here we go. So where they intersect, this is the point. This is my point. Okay, and then we have also another point where we have T02, and this is TS3, so that's my point again. Let's do that for TS3. For TS3 we have, sorry, or T03 we have 3 steady states, TS4, TS5, and TS6, and there we go. There's 1 point, second, and the third one, and let's continue doing so. Okay, very good, excellent. So we continue doing the same for all the points, and we get this lovely figure between TS and T0. Okay, let's understand this figure in terms of operation. So let's assume we have a CSTR which is run adiabatically, and we started up the CSTR. We start up the CSTR. We can start it up with the pure solvent, constant volume, and we continue monitoring the reactor. Obviously, the temperature inside the reactor will start changing until the temperature inside the CSTR reaches the steady state value. That is when the system reaches a steady state, because during the startup, the system is not under a steady state. So let's wait until steady state is reached after the startup, and obviously when it reaches the steady state, we'll see that the value of the temperature inside the reactor is TS1 for the case where obviously we have the feed temperature is T01. Okay, so we are here. Let's increase the feed temperature slightly. Okay, let's say we increase it till here. Of course, the system is not under a steady state for a while until it reaches the new steady state. Okay, and this new steady state temperature is slightly higher than the previous steady state, and let's continuously increase the feed temperature. So we increase the feed temperature slightly and wait until steady state is reached, and then we increase it again. Steady state is reached, okay, and until we reach the T02. This is the feed temperature, T02. Okay, in this case, obviously we reach what is known as TS2. This is the steady state temperature inside the reactor for this feed temperature. Okay, let's continue increasing the temperature. So every time we increase the feed temperature, the steady state temperature inside the reactor increases. Yani the temperature at the steady state will be higher than the previous one. So with every slight increase in the feed temperature, we have a slight increase in the steady state temperature inside the reactor, and so on. Let's continue doing so until we reach to T05. In this case, we have the TS10. We have TS10. Okay, let's see now what happens. Now that I'm in T05, I would increase the feed temperature slightly, just slightly. And guess what? Do we have also just slight increase in the steady state temperature, or it's a huge jump in temperature? You can see that the jump in the steady state temperature is huge. So with that little increase in the feed temperature, just slightly above T05, slight increase, the system actually will go to its new steady state. However, this new steady state is not reached very fast, just like before, and it's not slightly the temperature, it's not slightly higher than the previous steady state temperature, but it is much higher than the previous steady state. This is the previous steady state, and this is the new steady state. And it will take some time because the gap is huge, right? So you'll see that, whoa, everything is going out of your control. The temperature is going up and up and up, and it's not stopping. You expect it just like before. It will increase slightly. Okay, that was the case when we increased the feed temperature from T01 to T05. The increase in the steady state temperature was slight. However, now it's going up and up and up and up, and until finally it reaches a new steady state with a steady state temperature that much higher than the previous steady state. Okay, so basically what happened, I ignited the reactor. Wow, ignition took place. Okay, hopefully nothing serious happened. طيب, let's continue looking at this figure. So now that I'm here, okay, I could actually go back to T05 again, and this is what I get. Here. I don't go back here, it just slightly goes back. Okay, if I increase the temperature to T06, then I go to this steady state, which is TS12. Tamam. So again, now there is that slight increase in steady state temperature with that slight increase in the feed temperature. Okay, we increase the T0 slightly higher, the temperature, steady state temperature will go slightly higher. Again, I can go to T06, and again you can see slight increase in steady state temperature. Okay, now that the temperature inside the reactor is very high, I decide to go slowly back. So let's go slowly back, decrease the temperature from T06 down to smaller values. As you can see, with every slight decrease, okay, every slight decrease in the feed temperature, the steady state temperature goes slightly lower and lower and lower. Okay, and in this case, as I said, we can, if we change from T06 to T05, I go down from this is steady state to this is steady state. And then if I go down again to T04, okay, that steady state temperature goes slightly down and so on. Oops, maybe this is, yeah, here, tamam. And I go back to T02 and here I am. Okay, طيب. Now shabab, let's slightly decrease the feed temperature from T02 to slightly lower value. If we decrease it to a slightly lower value, tamam, do you have any slight change now? Any steady state here? No, we don't have any steady state here. So basically, if I go here, tamam, the only, as you can see, the only steady state value is, if I decrease the temperature to lower than T02 is here. So now, again, let's look. I was here at TS3, and now with a slight decrease in feed temperature below T02. Now I don't have any steady state except that a lower steady state here, a lower steady state. Okay, and you can see that again we have a big jump in the temperature inside the reactor. It's just a big drop in temperature. There is no steady state temperature just next to TS3, no lower one. The only lower one is way lower, so a sudden drop in the steady state temperature inside the reactor. And what did I do? I just simply extincted the reactor. Extinction took place. Okay, so a sudden drop in the steady state temperature inside the reactor. Okay, طبعا during the transient time, the temperature is decreasing from TS2 to lower and lower and lower and lower and lower, but it's not stopping, and lower until it reaches the new steady state here. Okay, so it continues dropping, and this will be out of your control. Okay, it will be like going fast to the new steady state. Tamam. Okay, so it might take a while to reach that new steady state, but it's continuously going down. Okay, so what if I go back again to T02 exactly? Would I go up? No, it will not go up. You just go back to TS2 again. Tamam. So basically you had a big drop in temperature from TS3 to TS2 where extinction took place, and then any further decrease in temperature will cause a gradual decrease in the temperature inside the reactor, the steady state temperature inside the reactor. Okay, until I go back to T01, the feed temperature, and then here I go back to TS1. So I believe now the concept of steady state, of ignition and extinction is very clear to you. Okay, so let's see, let's give some names here. Let's blame some people here. Right, so T05, in this case, T05 is called the ignition temperature. So if we want to blame anyone, so let's blame the T0, the feed temperature. It's because of the feed temperature this ignition took place. Okay, and in this case, the ignition took place after the feed temperature increased slightly above T05. So here T05 is called the ignition temperature. Who caused the ignition? It is T0. at the value when it was at the value of T05. So be aware of this guy. Be aware of this guy. It's an ignition temperature. While T02 is called the extinction temperature. See, when we operated at the upper steady state, okay, here, when it was T02, and this was the steady state temperature, a slight decrease in the feed temperature below T02, this can cause extinction. So be aware of this guy. Which guy? T02. Let's give him a name. Let's give him a name of the extinction temperature. Be aware of this guy. He is the extinction temperature. Tamam? So we blame the person or the variable which caused this ignition or extinction. In this case, they are the feed temperature. With a slight change of these guys, we had a sudden change in the steady state temperature. In this case, we discussed how ignition happened and how extinction happened as well. So we must, in fact, if you want to operate at the upper steady state, okay, we must exceed a certain feed temperature to operate at the upper steady state where T and X are higher. You can see T and X are higher compared to the case where we're operating at the lower steady state. Okay, with this we reach the end of segment 1 of lecture 51, and hopefully now you grasp the topic of ignition and extinction, and you know now who to blame. We'll meet soon in segment number 2 to explain further about this phenomena and learn what it can cause. See you soon.